Cast is now starting. All attendees are in listen-only mode.
Good morning, everyone. Hope everybody's getting started on a wonderful day. Welcome to our webinar on how to get the most out of your MTDR, a very important tool in our industry. There's just no better tool out there to test cable integrity than a MTTR. And if you don't have one, talk to your boss about getting one because these are very crucial to efficiency and finding problems and exactly where the problems are. Before we get started, I just want to say today, thank Chuck for being our presenter today. Chuck Phillips of Springbok Instruments. Chuck has a long history of experience. He's been providing training for decades, and he's a subject matter expert regarding the interpretation of MTDR measurements. But before we get started, I just wanted to talk a bit about the benefits of SCTE. I was looking at the website this morning and came across what's called Cortex Virtual Learn. And in this area of training, they have lightning modules. So if you just want like a 10-minute training on a topic that you're interested in, they have those available. They also have ebooks available. And then there's a feature called Network Sim with 3D simulations to pique your interest a little bit more. In addition, I'd like to talk about some upcoming events with the Golden Gate chapter. On January 23rd, we have our networking event at a DoubleTree in Pleasanton, California. That's near the 580-680 exchange. So if you're interested in networking with some of our local industry leaders, please get RSVP'd for that. On 218, we're working on getting a webinar set up. Should see an announcement out soon on that. That's understanding HFC power supplies. So we're going to review or do some basic training, but actually there's a lot of people think they know power supplies, but if you go in the details, it's like there's still a lot to learn there. On 423, we're going to have our Vendors Day and golf tournament. So that will also be at the Pleasanton DoubleTree this year. We usually have it in Concord. It will not be in Concord this year. So keep in mind these upcoming events and be ready for that. And with that, one more thing. We have some polling questions. So Chuck's going to pause me, and then I'm going to put those up, and you'll get a chance to vote on the answer. So we'll see what you're learning or what you know about MTTRs. And last, Chuck, do you want me to pause for questions, or you want me to read out questions at the end of each section? No audio. Check your mute. It's working a minute ago. Still no audio. Tap on the mute button and untap it on the GoToMeeting, because I've had that problem before where everything just stopped all of a sudden. I had to go in and mute and unmute, and it came back. So we're going to pause a minute, folks, while we try to work out this technical difficulty. Nothing yet. Does anybody else hear Chuck, or is it just me that can't hear him? Check your settings. I got a note from someone said check your settings. I had to readjust mine to here. Let me double check here. Again, if you can hear Chuck and I'm not hearing, please put that in the chat so I know it's working or not working. Yeah, nobody can hear Chuck. It says muted by organ. Okay, they're muted by organizer. So nobody can hear Chuck. Yeah, it was working just a minute ago, so I know what happened. If you have to, Chuck, log out, log back in, and we'll just everybody. So I'm sorry, folks. Just a last minute technical glitch. Yes, I do see some comments about participants. Yes, participants are muted. Presenters usually aren't muted. We come on unmuted, and then we can unmute participants. We don't usually do that because there's usually somebody's not muted.
Can you hear me now?
Yeah, yes, that did it.
All right. Now, what about the sharing of the screen?
I think I have presenter panelists. So try that now. Do you see
it? Coming up.
Okay.
Yep. Can you still hear me?
Yeah, still hear you. We're good to go there.
All right. Can you see my screen? Give me just a second here while I go full screen mode. Can you see my full screen?
Yes.
Okay. One more thing. One more thing. Can you see my whiteboard?
Yes. Got
okay,
your whiteboard. That's a great thing about Chuck. He likes to use a whiteboard, and I'm sure all of us people paying attention enjoy that because it gives it the more like in-person feel. So Chuck, it's all yours. So I'm going to go on mute and turn my camera off. So get started again. Prompt me when you're ready for questions. I don't remember your answer. Do you want me to pause you as questions comes in, or you want to you want me to wait till till you finish a section before I read out any questions?
So I'll prompt you for the first section. I'll prompt you for the first question, and then I'll prompt you for the second question. I don't remember the questions, but fortunately I know the answer, so we'll get to that when we get to it.
Yeah, so what about if the audience asks questions?
By all means, feel free to unmute and ask the questions. Let's make this free form.
Okay, got it. Okay, I'm gonna.
Okay, thank you everyone for your patience. Sorry for the glitch. What can I say? It happens. It's technology. So if any of you are familiar with me, or if you're not, my name is Chuck Phillips. I've been working for Springbok for I think about 5 or 6 years, but before that I spent about 20 or 25 years with Riserbond, and I've been working with SCTE my entire career. So I like to let everyone know, whether I'm doing a training session in person or online, this is not intended to be a brand specific training. So honestly, I hope even if you're not using a Springbok TDR and you're using one of my competitors, whether it's Tempo, Megger, or if you're using one of the modules on one of your multifunction units, I hope you come on board, because there's something that everybody can learn. Because the truth is, there's a basic TDR technology that applies to everyone. And in most cases, whenever I first start off my training sessions, I let people know, most people were never trained on much of their test equipment. The way most people were trained was, here you go, good luck, call me if you need anything, right? So I'm well aware that a lot of people have never had TDR training sessions. So since this will apply to every kind of TDR, I want to make sure that we start off really basic. The first thing that I want to talk about is, since most people were not trained, there's the fundamentals to how the TDR works. And I want to spend at least the first 15 minutes talking about the technology behind how it works so that you can understand what it's looking for, and in many cases, what it's not looking for. It's not uncommon that people have called me up after they purchased one of my or any other TDRs, really frustrated because they spent half a day troubleshooting, they can't find their problem. Come to find out, what they were looking for was not actually a TDR related problem. So we're going to talk about that, and then we're going to talk about a little bit of button pushing and how it relates to your specific TDR. But again, if you're using a brand other than mine and you want to either send in a question or make sure you get my contact information, you can call me anytime and I can let you know how that applies to yours. Then we're going to analyze waveforms, because when it comes down to it, that's the part that is the biggest problem. Once you learn how to push the buttons, it's learning how to analyze the waveforms. And I want to make sure a couple things that everybody understands about analyzing waveforms. One, if you are at all familiar with a TDR, I like to ask a question: would you agree with this statement I'm about to make? If you know what you're doing, most things that you're looking for are easy to find. Would you agree with that? That's if you know what you're doing, right? The whole purpose to analyzing waveforms is to get something to stand out that is not supposed to be there. So the last part that I'm going to talk about is how to find some of those hard to find things. You've been out here 2 or 3 times. Why can't we find this problem? Honestly, chances are it's not the specific TDR or brand that you're using. It's that, oh, I didn't even know about that setting. No one told me about that. I understand. So that is what we're going to talk about for the very last part. And then, of course, we'll open it up for any questions. So first things first, if you are familiar with me, I like to use a lot of analogies, which I probably will, so I can get you to understand things in a better way. What does a TDR stand for? First of all, TDR stands for Time Domain Reflectometer. And traditionally, way back when, even before me, it was kind of loosely called a cable radar. So this is just to show you that this is some of the brands that many people are using or have used. You got my TDR Tracker Pro up here in the top left. This is the old traditional standby riser bond 1205, a very solid industry standard, as well as the Tektronix Tempo TV220. You got your Megger, one of your current tempos, as well as a Tektronix 1503C. This, for my money, is one of the best TDRs that was ever made. And in all honesty, all of our current line of TDRs really stand on the shoulders of this classic beast right there. So speaking of being called a cable radar, I like to use the analogy of a police radar gun, where you're going to connect your TDR to your cable under test. It generates a high frequency signal. It sends that signal down the cable. As soon as it finds an event, it reflects some or all of that energy back to the instrument. It takes the time that it took to get there and converts it to a distance, time domain reflectometer. Now, this may sound like I'm arguing semantics, but I want people to think of what the TDR is looking for as events, not necessarily faults. Because when people get it in their mind that it's just a fault locator, that's when some mistakes start to happen. I quite literally have had people call me upset, frustrated, because they spent half the day looking for what they were looking for, ended up digging up a perfectly good splice, and upset at me because they dug up a perfectly good splice. Really? Maybe if you would have sat through one of my classes, I could explain to you how to tell good between bad, because a TDR will find all things on the cable. Things that are supposed to be there as well as things that are not supposed to be there. So getting ready to jump over to my whiteboard here, specifically, again, thinking outside the box, a TDR can be used on any type of metallic cable that has at least 2 conductors. We manufacture TDRs for a bunch of industries other than just cable TV. So understand, I have a huge variety of customers that I sell to and train. So hopefully you can see my whiteboard. When I say a TDR can be used on any metallic cable that has at least 2 conductors with coaxial cable right up here, I'm referring to the center conductor versus the outer conductor. I began my time in the industry many, many years ago, back before gray hair, in the telephone industry, where we had twisted pair, have twisted pair. Your tip and your ring. It can be used on any of your in-home electrical wiring, your Romex cables, right? It can be used on Cat5, Cat6 cable. It doesn't have to be only 2 conductors, but it has to be at least a minimum of 2. No single conductor wire here. So anytime you have 2 conductors that run parallel together over a distance, they will naturally form an electromagnetic field. That electromagnetic field gives you a constant impedance all the way through. What a TDR is looking for is anything that interrupts that constant impedance. Now, you could say anything that interrupts the relationship of the conductors to each other, and while that is partially true, there's a little bit more to it than that. But as a for instance, if I look at my coaxial cable right here, and if I pinch it, well, at that point, the outer conductor is closer to the center conductor. Impedance mismatch, TDR sees that rather simply, right? On my next example of twisted pair, if you have one side open, well, that's an impedance mismatch, right? If the cable is completely cut, well, that's the easiest thing in the world for any TDR to see. If your cable is completely crushed, that's also the easiest thing in the world for any TDR to see. If you get water in the cable, get this. Even though the relationship of the conductors may not change to each other, what happens is, essentially, the signal is going down both conductors at the same time. And when water is involved, the signal attempts to jump from one conductor to the other. So that's why a TDR sees that as an impedance mismatch. If water can be pinpointed in a cable, there are many things that'll let you know you have water in a cable, but a TDR still is the best thing, bar none, for being able to pinpoint where water is. But also, typically when you have water in the cable, you're going to have 2 issues, right? Where it came in and where it migrated to. Still, TDR is your best friend. We have an issue in twisted pair cable, what we call splits and resplits. Picture if you have a 100 pair twisted pair cable that got damaged or cut at some point. Well, when somebody has to go in there and splice all those pairs back together, they're going to make a mistake probably and get one of those pairs crossed. We call those splits and resplits. And when you go back to add digital services later on, somebody has to go and find where those splits and resplits occurred. TDR is your best man or woman for that job. So understanding, let me throw out another example here because this is key later on since a TDR is looking for impedance mismatches. If you took a twisted pair cable, cut open the sheath and pull the conductors apart like this, again, a signal is still going to pass through that just fine, but you have changed the relationship of the conductors. So a TDR also sees that as an impedance mismatch. So let me ask you this, men and women. Let us say I have an entire roll or reel of cable that's manufactured improperly. The center conductor is off center all the way through. Does a TDR let you know that this is a problem? Now, many people will bounce this around and they'll come up with different theories, but since I don't have the benefit of looking at your face and you answering back to me, I'm going to assume some people are nodding yes and some people are going to be nodding no. The answer to the question is a TDR does not let you know that this is a problem. Why? Because even though this is clearly no longer a 75 ohm environment and this cable is seriously jacked up, a TDR still sees this as a constant impedance all the way through. It's not unlike looking down a railroad track and comparing one side to the other and it's saying, yeah, that's perfectly straight to me. It's got no idea if it's supposed to be this wide or this wide. It is still a constant impedance. Everything else still applies, right? Kinks in the cable, water in the cable, impedance mismatches between it. Now, where this can cause a problem, what if you have a fire? Oh, yeah. You get a fire, of course, and then if that dielectric melts and this happened, will a TDR see that as an issue? Most times, yes. But what about this? What if this distance that I'm talking about here, what if it's a 30-foot section of cable, and what if it is ever so gradual over 30 feet? Will a TDR see that? That's where it becomes some of the harder stuff to find. That can be really difficult, but sometimes it can depend on how close you are to it or how far away it is. And it doesn't necessarily figure that just because you're closer to it that you can see it. Sometimes you're going to want to get a better view from backing way off. And again, that could be one of the reasons why you can see some things from one side versus not being able to see them from the other. And of course, I'm always going to tell you to shoot from both sides, as are your respective companies, but we also know that we can't always get to both sides at any one moment in time. But nonetheless, that's what a TDR can see and cannot see. Let me tell you also where this sort of thing happens to me a lot. When I'm dealing with other customers, for instance, who use cables, trailer manufacturers use a lot of cable. Airplane manufacturers, if you can imagine a jumbo jet airplane, they have every possible cable in the world that you can think of: power cables, communication cables, fiber cables. I could easily have a mini RG59 cable like this that runs inside of an airplane. And at some point, that cable is going to get too close to possibly a motor or a light bulb or something. So when I'm teaching them to use a TDR for the first time, I let them know, I see the problem right here at 22.5 feet. They pull that cable out and they're like, I beg to differ with you, homie. There's nothing wrong with this cable. And I'm like, yes, it is. It's on the inside. Trust me. And don't call me homie. Okay, back to the presentation. Although by the time we really bonded, you can call me homie. Okay, so the biggest thing that you're going to have to worry about as far as calibration on the TDR goes is going to be the velocity of propagation. Most people have heard of velocity of propagation, but let me just explain it to you in a real simple way. Velocity of propagation, or sometimes it's called VF or velocity factor. Sometimes it's just displayed as a 2-digit or possibly a 3-digit percentage number, or a decimal place number. It has to do with the type of cable that you are testing. Every type of metallic cable out there has at least a 2-digit VOP number that's associated. When I say at least 2, I mean sometimes it's 3. I don't care whether it's RG59, RG6, half-inch, inch, 2-aught power cable, 22-gauge twisted pair. There's at least a 2-digit VOP number that's associated with it. And this is all that number means. If we assume that the speed of light in a sealed tube is the fastest signal there is at 186,400 miles per second, and every other signal is slower than that, all VOP does, it represents a percentage of the speed of light. So if I had an RG59 cable that had an 85% VOP, that just means a signal will travel down that cable 85% the speed of light. Knowing that that's your cable and knowing that's your VOP, punch that into your TDR. Now your cable and your TDR are speaking the same language. What happens if you have the wrong VOP number set? You're going to be digging in the wrong spot, okay? So that's why that is very important. So when you go inside your TDR and you select the cable type, you will see on whichever TDR that you're using, there's a VOP number that's associated with it. That's all we care about, is just that 2-digit VOP number. The good news is that's the only thing that you have to worry about as far as calibrating your TDRs. In fact, TDRs don't actually go out of calibration, nor do they require recalibration. Oh, by the way, that's the good news about VOP. That's the only thing that you have to worry about on your TDR. This shows you quite literally the signal will travel at different speeds through different cables, right? Here's the bad news. The VOP number can change, and by the way, it does change. Age of the cable. Should stand to reason a cable that we buried 20 years ago is going to behave differently than one we just put in the ground last year. And I don't care where you're at, I'm quite certain you got cables a lot older than 20 years, okay? Temperature is probably going to be your biggest offender. It is going to be your biggest offender. And when I talk about temperature, I'm talking about temperature changes. And when I talk about temperature changes, I'm not talking about your morning to noon temperature changes in the springtime. I'm talking about your winter to summer changes. I'm located in Lincoln, Nebraska, so it is very easy for us to have 100-degree temperature changes from winter to summer. That's what I'm talking about. Clearly, it's going to affect your aerial cables more than your buried, but for any of my customers in Minnesota or the Dakotas or Canada or Alaska, where the ground temperature, where the ground actually freezes during the wintertime, it can also affect your buried cables, right? Or even if you're in a part of the country like the South, maybe South Florida, for instance, where it may not get that cold for extended periods of time, think about this. Think about your aerial cables that are black, by the way, and they've been baking in 100-degree weather for days at a time. That can be a pretty good temperature change from spring to the middle of summer, right? So that's something that you also have to keep in mind, but we can account for that, which I'll go over later. Humidity clearly would affect your aerial cables more than your buried, but with coaxial cable, one of the reasons why it's lasted as long as it has is because it's shielded very well. It's a good medium to begin with, but understanding I do sell in other industries other than just cable TV, so it's more of a factor. Sometimes it can happen between different manufacturing runs. Honestly, that's not something that I see happen that much. Okay, so as an example, this is one of my TDRs, the tracker. You'll notice when you go into the VOP section and select cable type, they're typically sorted by brand alphabetically. You'll see your series number over here, and that 2-digit number is just right there. That's all we care about is that number, right? This is another one of my TDRs. And by the way, since we get these numbers from the manufacturer, let's say you have one of the newer TDRs out there on the market, either the Springbok Tracker Pro or perhaps one of the new Tempo TV220s or something like that. Since we get these numbers from the manufacturer, if you're using an older TDR and you don't have one of the cables listed in your menu, call one of your buddies that has one of the newer TDRs and just say, hey, do you show a VOP for a QR cable? And that'll be good enough to get you going. Or if you're doing some work on the side and you're helping your buddy with his electrical wiring in his house or something, you don't know a VOP number to that, contact me. I do, all right? There's a slide that I skipped in there accidentally. That's okay. Okay, now, this is where the rubber meets the road. And this is actually the part that most people didn't learn. And by the time we get through this section, you will probably have some aha moments as to, I wonder if that problem I had last spring was this problem, because I did not know that this is the way this worked. Let's talk about pulse widths. This is how the TDR launches its signal. Now, a couple of things I want you to understand about the TDR. It is a time-based instrument. That's why it's measured in time, nanoseconds or microseconds. But there's also a frequency factor to it, which I will explain coming up here shortly. Oops. But first, for those inquiring minds that want to know, let me tell you what the TDR is doing behind the scenes. The actual output pulse or signature that you see on the screen, we designed these by using an oscilloscope. So all you're actually looking at is a sine waveform, but we've cut it in half and we're only allowing you to see 1/2 at one time. So any reflections that go up are an open or a raising of the impedance, and anything that goes down is a lowering of the impedance. Most TDRs, and I have to qualify this by saying most, because most TDRs have a variety of pulse widths that you can choose. Some of them only have one or possibly two, but just in general, this is the way it works. I like to use the analogy of the way the TDR is launching its signal is if you take this rope and flip it on the ground, and you know how that wave travels down. If I give that rope a lot of energy, it's going to go a long ways, right? Versus if I give it just a tiny flick of the wrist, it doesn't go as far. So you could say that your larger pulse widths are for going longer distances or for testing longer lengths of cable, and your smaller pulse widths are for testing shorter lengths of cable. Also partially true, but there's a little bit more to it than that. Each individual pulse width, and this is just a variety of pulse widths from small to large. Nobody's TDR has these exactly, but it's going to vary somewhere in there. Each individual pulse width has at least two things that are associated with it. A maximum footage range, how far it will go, and a blind spot or a dead zone. Let's talk about maximum footage range first of all, but I want to start off by asking you a question that I want you to ponder. Can a TDR see through taps? Hopefully you're nodding your head yes, a TDR can see through taps. Can a TDR see through amps? No, a TDR cannot see through amps. However, a TDR can typically see 2 amps, meaning you'll recognize the signature when it gets to an amp. So it can see to it, but it's not going to see through it. Can a TDR see through DCs? Splitters? This is where it gets a little bit hairy for some people, because the truth is a TDR can see through splitters. But the problem is that once it gets to a splitter, it's going down both legs at the same time. So it can see through splitters. The problem is once you see the signature of what the splitter looks like, from where you're looking, you can't tell which leg it's going down, right? So from here, you don't know where it's going, but it is going down both legs at the same time. So a TDR can see through passives. It cannot see through actives. I point that out because the pulse widths that I have listed here, when we talk to maximum range that will go, these numbers are abouts. So I don't want you to get married to exactly how far a signal will go, because there are so many variables that cause that to happen. But let's just talk about this for a second. Let's take an average small pulse width, which is about a 2 nanosecond pulse width. Sometimes I've seen a 2 nanosecond pulse width go in other applications as far as 3,500 feet. You know, in other industries, we don't have amplifiers stopping it. So I've seen it go as far as 3,000 feet, and sometimes I've seen it go only 200 or 300 feet. I point that out because if you ever see your 2 nanosecond pulse width, or any pulse width for that matter, only going a couple hundred feet, you need to ask yourself, why is that? That's really interesting. Why is my signal only going so far? Maybe my F or my B and C connector right here, maybe it's loose. And mine is loose right now, by the way. Or maybe this F connector is failing or has failed. They do fail, right? Maybe I'm using the same jumper cable that I started using when I started in cable TV 15 years ago. Don't be that guy or woman. Maybe that first reflection that I came across on my TDR screen, maybe that's a splitter, a DC. Because doesn't that stand to reason to a TDR if my signal is going to go down both legs? Isn't that kind of similar to losing half my signal? To a TDR it is, right? Or maybe that first signature that I'm coming across is water. Everybody always wants to know what the shape is like. I want you to pay attention to what the signal's doing, right? So water is going to suck up your signal like a son of a gun. So maybe that's where my water problem is. But regardless, we understand maximum footage range. Also, this is something that a lot of people get confused on, understandably so. You may also think, if most of the time I'm shooting, I'm only going up to about 1,000 feet most of the time, and if I rarely ever shoot past 2,500 or 3,000 feet, you may look at this chart here and think, well, shoot, I may never need to go above a 2 or a 25 nanosecond pulse width because we don't have cable runs out to 10,000 feet. I do in other industries, right? But also understand this. What if you do have a water-saturated cable? If you do have a water-saturated cable, you should think of your cable signal as, maybe I'm going to need more power to get through that, right? So sometimes you may need a 25 or 100 nanosecond pulse width to push through a lot of crap on your line. So we understand maximum footage range. Let's talk about blind spot. Again, since this is a time-based instrument, the amount of time that it takes for the signal to launch can also be equated to a distance, and that's what we call a blind spot or a dead zone. So if I have, back to my chart, apologize. If I have, for instance, 100 nanosecond pulse width, it's going to take 50 feet for that signal to launch. So if your TDR only had 100 nanosecond pulse width, or if you were accidentally in the 100 nanosecond pulse width and didn't know it, if it takes that signal 50 feet to launch, imagine if you had a buried pedestal right here, okay? And if you were connected right here, you weren't seeing the first 40 or 50 feet of your cable. What are the odds you could have a problem somewhere in here? pretty high, right? So that's when we would always tell people, make sure you're using at least a 50-foot jumper. So by the time your cable signal is live, you're seeing everything on your cable. Now, hopefully, hopefully common sense would have kicked in about that time, and you're also going to go back to the other end and shoot back, but not necessarily just so you can get closer to the other side, but so you can back up and get a better view. Now understand, over the years, we in the TDR industry have improved upon these pulse widths. And then eventually, most people got down to about a 5 or a 25 nanosecond pulse width, which had a blind spot of somewhere between, maybe 5 or 15 feet. Many of your common TDR manufacturers now have a 2 or a 5, which is going to have a maximum of about a 5-foot blind spot. That's when it became the industry norm to tell people a 6-foot jumper will do. That's how we got there. Now, over the years, Tempo Greenlee eventually came out with a 1 nanosecond pulse width. Riserbond eventually came out with a sub-nanosecond pulse width, sub meaning less than 1, where they had blind spots as small as 6 inches to 1.5 feet. Now, I got to be honest with you guys. I'm not telling you the reason why you now have a 6-inch jumper is so you can use a 6-inch blind spot, so you can use a 6-inch jumper, because you're going to look a little bit silly here, connected with a 6-inch jumper and trying to see your TDR at the same time. That's not why I'm telling you that. I'm telling you that because if you have ever been out in the field, sorry about that. Putting my phone on Do Not Disturb. If you have ever been out in the field, bear with me, and you've been here 2 or 3 times, you've been out there, you found your first problem. Everything was cool. It was working just right. Your TDR was working well. You had your best knowledge going for you, and you are the man that is doing this. But if you've ever found a problem, dug it up, fixed it, turned your TDR back on, and you still had the same or similar problem, this is one of the reasons that can happen if you're using a TDR. Using an example of a section of cable that is 200 feet long. That's 200 feet, not 2001. And let's say I had 2 events in the center of the cable. Let's call it 2 splices. One at 100 feet and one at 105 feet. 2 events 5 feet apart. If they were splices, would you agree that they should look something like this? This is supposed to be a backwards S-curve, by the way. Splices look like a backwards S-curve. By backwards, I mean it's going to go down first. One at 100 feet, one at 105 feet. But when you actually turned on your TDR, it didn't look like this. When you actually turned on your TDR, it looked like this. One event right at 100 feet. Why? Well, because you didn't know this or you didn't realize this. Perhaps you were in a 50 or a 75 nanosecond pulse width, which had about a 20 or a 25-foot blind spot. So understand, the rope analogy, this wave going down the cable, it's not just at the very beginning, but it's going to be similar as it goes down the cable. This is almost quite literally a 25 or a 30-foot wave that's going down the cable, right? So, pardon me for turning this off here. So that's why this looks like this, because there was a second event that was only 5 feet away, but it was lost in the shadow or the wave of that. That's one of the reasons why most people miss multiple faults, because they weren't taught about the blind spots of each individual pulse width, right? So the moral to that part of the story is make sure whichever is your smallest pulse width that your TDR has, make sure you start off in at least the smallest pulse width so that you can see multiple faults close together. Make sense? Now, here's what's interesting about this. It's entirely possible that that scenario that I just presented to you may not, in fact, look like this. It could look like this. Come on, don't mess with me now. I'm calling this reflection right here a double hump, okay? different TDRs use a different software program where we connect the dots basically on the screen. So some TDRs draw their waveforms more sharp and have a point to it, and some are just a little more rounded. But regardless, all of your reflections do tend to rise and fall rather smoothly. So if you ever see a signature that looks like something like this, where it looks like something could be interrupting your signature, I want you to assume something could be interrupting your signature. So if I were to able to use some sort of zoom window here and zoom in on that and expand that picture, I might find that upon closer look, closer evaluation, that there are actually two events in one here. If I were to spread that out, I could see that there were two separate signatures. Or if I saw something like this, I might look at my TDR and say, oh shoot, I'm in 100 nanosecond pulse width. I didn't even know how I got into 100 nanosecond pulse width. Just by backing that down, 175, 50, 25, just by backing it out might suddenly start to make that expand and you see two separate events, okay? Now, a lot of people were never taught about this, but the very first time you turn on your TDR, if you are looking at it right now, you're gonna look somewhere down in the bottom center or bottom right-hand corner. The pulse width is right there. Now, here's the deal. By all means, screenshot this if you like, or later on ask me to send it to you. I don't expect you to memorize this particular chart. All I want you to understand is that most TDR start somewhere between a 1 and a 5 nanosecond pulse width on the small end, and it's going to have a blind spot of up to about 5 feet, and then it just goes up from there. That's all I want you to keep in mind from that. Understood? Good. Okay, so now, before we start to get into explaining what a few different features are, I'm going to ask Woody if he would ask our first question.
Okay, just give me a second, folks. I don't do this every day, so here we go. Our first question will be, what principle does a TDR work on? So we have 4 choices: radar, light, sound, ESP. Hopefully you guys can all see that. I know you can't see it, Chuck, but I do see poll in progress, and we have, yes, I do see it was covered up, but I do see people voting, so we'll give it a second here.
All right.
So looks like we have almost an even split between 2 answers, none on one and a few on the other.
We'll give it another few seconds.
We've got about half the folks that voted, so yeah, we'll give it a couple more seconds. Now, if I can just remember how to display the results, I think I have to close it first, then I do. So we're stuck at about 51%. We'll close it now, and we will display the results, I hope. Let's see here, share, there we go. Okay, so the answers came out: radar 50%, light 44%, sound 0%, and ESP 6%. So we'll let you expand on that, Chuck.
Okay. So one of the things that I said from the very beginning is a TDR, especially a pulse TDR, it works on the radar principle. Remember, I used the example of it's very similar to a police radar. So the answer is radar principle. Now, what's interesting is that I can see how someone might confuse it as light, because this is an MTDR, not an OTDR. But an OTDR, of course, stands on the shoulders of an MTDR. The MTDR is the original TDR. And you will find that a lot of things that you learn in this class will apply later on, but there are similarities, but it's not the same. It's not light, it's radar. Make sense? Okay, now, getting back to the presentation, one other thing I forgot to mention that this is very key later on. I mentioned that each individual pulse width has at least two things that are associated with a maximum footage range and a blind spot. Another thing that I want to point out is the third possibility, the frequency part. A TDR, of course, is also based on frequencies because all things are frequencies. But let me tell you how that applies. Not uncommon where people will ask me, Chuck, what frequency does your TDR transmit at? And it doesn't matter where I've worked or when this question comes up, but in all honesty, most times when people ask that question, it doesn't actually matter what they're trying to apply it to. But let me tell you where it does matter. First, a TDR does not generate a frequency or a specific frequency, a specific tone, all right? So you need to get that out of your head. What a TDR actually does is it launches a pulse. What's a pulse? A pulse is a burst of frequencies. So it is frequencies, but it's a burst. It's a very wide range of frequencies. Each individual pulse width does have a fundamental frequency that's associated with it, even though it's a wide range. So the reason why my lower pulse widths go farther is because they contain a burst of lower frequencies. Lower frequencies travel farther. The reason why my smaller pulse widths don't go as far is because they contain higher frequencies. Higher frequencies don't travel as far. Big however, if you are looking for the smaller problems that plague your higher bandwidth, it's the smaller pulse widths that are able to find that. What types of smaller problems am I talking about? I'm talking about rodent chews. I'm talking about water in the cable. I'm talking about little teeny tiny hairline cracks in the cable. Yes, a TDR can find that, but if you are in one of your larger pulse widths that contain the lower frequencies, it's going to shoot right over it, and you're not even going to know that you missed it, right? So that's going to be why a lot of TDRs, some TDRs cost more money than others. It's not because they're more accurate, but because they contain smaller pulse widths, have higher frequencies, would find your smaller problems. If you're looking for just cuts in the cable, the most obvious things to find, any pulse width is going to be able to find that. Any TDR is going to be able to find that. Stevie Wonder can find that, okay? But you're going to need the smaller pulse widths to find those smaller problems. Now, moving on. Before I start to get into what analyzing some of the waveforms looks like, there's one other feature that I want to make sure that I talk about on my whiteboard that gets missed a lot. Most TDRs, and I say most because there's some entry-level TDRs that don't give you this flexibility, but most TDRs have this thing that we call V gain or vertical gain. Let me explain that really quick. When you first turn on your TDR and you have a pulse width like this, this represents the output pulse or the start of the signal, the B and C on the front or the back of your cable, your TDR, and then this would represent an open at the other end of your cable. It's disconnected, right? Everything in the middle right here, this line is flat. In a perfect world, a flat line means there's nothing wrong with your cable. When little shapes start to appear, that's when we start to analyze, well, what is that shape? And I'm always going to tell you, I want you to be more concerned with where it is, not necessarily what it is. I'll give you tips on how to figure out what it is. But the bottom line is, if the line is flat, that means there's nothing wrong with the cable until you start to really analyze it. When you increase your vertical gain, that begins to increase what I like to call the vertical volume of that line. So you're turning it up to see if you can see something that could be hiding in that line. As you start to increase your vertical gain, you can make a completely good cable look bad, right? And by the way, I promise you that your supervisors know this trick, so don't try and pull that on them. So clearly, the more you turn up your vertical gain, the more you can get things to stand out. Not uncommon, then somebody will look at this line and they'll tell me, so what is that? Well, from this standpoint, I can't tell you what that is. It could be AC. It could be RF. It could be nothing at all. It could be that your vertical gain is just too high, because the question that I'm going to ask you is, on this line or on this line, does anything stand out from the rest of the line? And it doesn't. It's entirely possible that this line and this line and this line are all exactly the same, just with the vertical gain turned up too high. But put another way, you could also increase your vertical gain, still make the whole line look ugly, and then I'm going to ask you at this point, does anything stand out? Well, you better say that this does. And it's entirely possible maybe this could be where your water starts, and maybe this could be where your water ends. But your vertical gain is going to be how you try to get that to stand out once you've got things started. Now, the next general question that a lot of people will ask, okay, so what should my vertical gain be set at? The thing that I'm always going to tell you is I don't care. It doesn't matter. Whatever it takes to get something to stand out that is not supposed to be there. So let me give you a few examples of how this works in the real world. That wasn't right. Sorry, I should have already had this open. This is my first presentation of the year, so you guys are getting me straight off of vacation. So any mistakes I make, I apologize. Okay, so this is just a random waveform that I shot a few years ago, and I want to show you how this will start to look. Let's pretend that this is actually our TDR test. Now this one I actually shot a few years ago with a riser bond TDR. But let me show you how we begin to analyze it. So first things first, you will see that I have my output pulse over here on the far left and the end of your cable on your far right. Whenever you start to use your different features on your TDR, such as your range button, range is your more cable, less cable button. So if you know that your section of cable is 300 feet long, but all you're looking at on your screen is 50 feet, you're going to want to use your range or your more cable button to try and bring that into the cable on the screen, right? So a few things I want you to be able to see right here. This shot was in a 2 nanosecond pulse width. So again, with the chart that I showed you before, we know that this is on the smaller end where we're going to be able to see our small problems, right? And since I can also see the end of my cable, there's a good possibility I'm not going to need to shoot this in another pulse width. So to see what it is we're looking at here, I can see that the end of my cable over here is somewhere between 300 and 342 feet. So I'm going to take my second cursor and I'm going to place it right on the front leading edge of that reflection. I don't want it at the peak and I don't want it at the trailing edge. I want it at the very beginning right here. So I can see that this cable is 338.8 feet long, right? As you can see, this line is perfectly flat, which might indicate there's nothing wrong with that cable, but that's before we start to analyze it. You can see that my vertical gain is all the way down, so let's just slowly start to increase the vertical gain. Now, whether you're connected live or you're looking at an uploaded waveform, a stored waveform, or an uploaded waveform on your smart device or your computer, I want you to resist the temptation to just start cranking the vertical gain and zooming in because you might start to miss stuff. So I want you to go slowly. When I say slowly, I mean deliberately, because we don't have all day to do this, especially if we had to turn the customer off to shoot this. So as I start to increase my vertical gain to what? It doesn't matter. Let's just go notch by notch until I start to see something. So clearly you can see something is amiss right about here. So I'm just going to go just a little bit further. And this is as far as I need to go before I do this. Especially if you guys are connected live, I need you to understand something. If you see something that you want to take a look at later, I want you to get in the habit of marking it first. If you have like a second cursor or a marker or something, I want you to mark it first. Why? Because you're looking at a live waveform here. And let's say you were looking at something that could be possibly intermittent on a windy day or something like that. Sometimes if you guys get in the habit of zooming in or zooming out too quickly, you can accidentally shoot something off your screen, and then when you go back and try to find it again, and it's already 20 degrees out and you're freezing your buns off, if that could have been your problem, but you accidentally shot it off the screen, you are going to be so mad. So get in the habit of marking it first, just in case. This is a static shot, nothing's going to move, but I just want to impress upon you, mark it first. So I have now marked this because it's obviously the start of the most severe part of the cable. Now this is what I'm going to do. I'm going to start to analyze it. So I am literally going to zoom in a little bit, increase my vertical gain, zoom in, increase my vertical gain. I want you to think of actually sculpting something here. This is an art, okay? And the more you do it, the easier it gets. So as I start to zoom in just a little bit further, this TDR zooms to and from the center of the screen. So I have to sometimes zoom in, move it over, zoom in, move it over. So as I start to increase my vertical gain, and when I mention to you what does the vertical gain need to be set at, whatever it takes to get something to stand out, I will prove to you that there is a point where it's too much and a point where it's too little, and it's really obvious, and I'll make sure you understand that. So from this point, this is as far, that's a little bit too far, this is as far as I need to go before I can determine clearly this is two separate events. Does everybody see that? I have an S-curve that ends right here and another S-curve that starts and ends right here. The first one is at 84.2 feet. The second one is at 89.8 feet. Two separate S-curves. Now, let me jump straight to the end and tell you what this was. This was actually two dings in the hardline cable. It was that easy to find, but I was in a 2 nanosecond pulse width, all right? Can you understand how if I were in 100 nanosecond pulse width, how I might not see something that small? But can you see how if maybe this were in maybe a 25 nanosecond pulse width, how I still might see it, but at a few feet apart, it may only appear as one. You see what I'm saying? So that's what this problem was right here. Now let me show you some other things about this particular waveform as I'm looking at. First things first, let's talk about vertical gain. As I mentioned, there is a point where it is too little right here, right? And if I crank it all the way to the top, clearly that's just a bit too much, right? So somewhere in the middle is where you have to get this to where it makes the most sense to you. And if you're turning this into somebody else, this is where it also gets a little bit funny. If I crank this too high, you would be amazed at how many times I will have people say, well, yeah, that's all fine and dandy, but what about this? And what about this? And what about this? And I'm going to be like, yeah, what about this over here? And then somebody's going to say, well, what about this? And I'm going to be like, really? Is it not obvious that this is the most part? So I like to keep my vertical gain in the range of what I call, don't you worry your pretty little head about, okay? So if I make it clear to the person that's going to repair this, make sure your vertical gain is at a point where it's manageable for them. Because in all honesty, you see this little ripple right here? It's probably nothing. Go with the most obvious first. Don't worry your pretty little head about all this other stuff if this is obviously the worst part of the problem. Now, let me talk about something else while I have this particular thing on. I get a little bit wordy, so I want to make sure that I don't go overboard here. So again, we already proved that the end of this cable, because we checked our map and we disconnected, we verified, it's 337 feet long. I'm going to zoom past the end of my cable here. If that is the end of my cable and there's nothing else past that, does anybody know why I can still see things past the end of my cable, which should be disconnected? What are these called? They're called reflections or ghost reflections. The reason ghost reflections happen is because a TDR is sending out a pulse. What's a pulse? Well, a pulse is a certain burst of energy, and it's sending it out several times per second. How many times per second? Well, however many cycles per second the pulse width is based on, right? So all of these other reflections are just echoes, 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 echoes of that original pulse. Okay, it's just residual leftover harmonics. This is just a reflection of the end of the cable right here. We suspect it's a ghost reflection. Why? Because for one thing, it's exactly twice the distance. I don't need to measure this to find out it's exactly the distance, right? It also tends to reverse polarity, and it also tends to get smaller in attenuation. They tend to happen the most on your smaller pulse widths, which contain the higher frequencies. They tend to happen the most on shorter lengths of cable. What am I calling shorter? 1,000 feet or less. They also tend to happen the most at the end of the cable. Now, did anybody notice that I was just speaking like a salesman right there, right? So that tend to happen like this, and results can be as much as people are saying. The reason I say that is because that's not always the case. But let me ask you this question first. I just showed you an example of how ghost reflections happen after the end of your cable. Have you ever seen ghost reflections happen inside your cable under test? And if you haven't, I just want you to pay closer attention, because chances are they have, but you didn't know it. And if you have, I'm going to ask you a question: how badly do they suck? Well, they suck a lot, but let me tell you why. Now, I don't have a good waveform example of where I shot ghost reflections right now, but I'm going to create one for you. I already told you that this is my cable under test. Output pulse, end of my cable right here. I'm going to overshift this entire waveform to the left. And I am now going to pretend that this is my output pulse and this is the end of my cable. So we already know that this is the damage right here, right? The reason I say ghost reflections suck, because I said this at the very beginning, most things that you're looking for are easy to find. Knowing that, this is obviously damage, but you would also look at this, and this is obviously damage as well. So if you dug up this hole right here, you would find your problem right here. But if you dug up this hole right here, this is where you start to get a little bit angry, because there's nothing there, and I mean nothing. Now, this is where this can throw you off. Everybody thinks that ghost reflections always happen double the distance, right? And they do, but you would not see this as a red flag, because this isn't exactly double the distance of anything, right? However, it is the same distance from here to here as it is from here to here. And if I told you, and look at my face for just a second here, if I told you that we suspected this might be a ghost reflection, what do you notice about this signature compared to this signature? Do you notice that it's a mirror reflection? So check this out. If you are looking at your cable and you see signatures that reflect each other, meaning it looks exactly the same, I need you to suspect that that could be a problem, okay? If you see this and it is a mirror reflection of another one, it could be a ghost reflection. If you see that, and it's exactly double the distance, bro, it's a duck, okay? So that's when you know it is definitely a ghost reflection. Now, what would be the simplest way in this scenario? If we suspected this might be a ghost reflection, what would be the simplest thing to do to rule that out? And what's funny about this, when I ask people this in person, a lot of people say, well, if you fix it, and then if the other one disappears, okay, yeah, but I need to go simpler than that, all right? The simplest way would be to go to the other side. Because if you go to the other side and shoot back and this suddenly disappears, not going to minimize, but disappears, and this is still there, boom, that was a ghost reflection. Now, I'm always going to ask you to go to the other side, but you can't always get there. But if it's going to save you from digging a hole, go to the other side. That also explains why sometimes when you are using your TDR, some things look completely different from one side versus the other. Now, let me ask you a really interesting question right here. I'm kind of getting into the weeds a little more than I wanted to, but clearly I'm on a roll. So check this out. What is the ideal jumper cable you should be using? That's kind of a trick question, because I was kind of leading to you believe that you should be using at least a 6-foot jumper. But understand, the actual answer to that question is technically whatever is your smallest pulse width blind spot, okay? But the reason why most TDR manufacturers will supply you with a 6 or a 10-foot jumper is because the truth is that's the smallest jumper that will do. for all of your pulse widths. But here's the deal. If I told you that there's another way to minimize ghost reflections inside your cable under test, would you take my advice? I would if I were you, because I've been doing this a while. If you use a longer jumper, that is another way that would make these ghost reflections go away. How long are we talking? You're probably not going to like my answer, so I'll just jump right into it and tell you. I'm going to say if you use a 50-foot jumper, at least a 50 feet, sometimes a 75-foot jumper, and all of a sudden it quiets down your line, this still appears in the same spot, albeit 50 feet out, and then this one disappears. If that saves your butt and saves you from digging too many holes, you might want to consider that. However, I don't want you to scoff or get angry at me. I'm not telling you you need a 50 or a 75-foot jumper all the time. I understand. I'm just suggesting if you're one of those people that finds out, I'll be doggone, man, I find a lot of ghost reflections. Make yourself an extra 50 or a 75-foot jumper to take along with you. And if you do see something that looks unusually noisy, pull out that longer jumper and see if it makes a difference. Just do it and take it with you, okay? All right. Now, before I get ready to go on to my next example, I'm going to ask Woody if we're ready for the second question. Let me rephrase. I'm ready for the second question. Woody, are you ready?
I'm going to launch it right now. Here we go. So what allows a signal to travel down a cable at different levels of energy and distance? So we have 4 choices: VOP, pulse width, impedance, and weather. So we got a few votes coming in. I'll go on mute and I'll just hang out for a second here.
I will also hang out.
We got 53% voted. We'll just give it another minute. That eclipsed our last vote total, which was about 51%.
Nice.
So we are getting almost everybody. Yeah, we're okay.
We're good.
So I'll go ahead and close that, and I will just share it with everybody. So looks like the vote went as follows. 21% voted VOP, pulse width 53%, and impedance 26%, and nobody selected weather. So
okay. Now, just for kicks, Woody, would you read the question one more time?
What allows the signal to travel down a cable at different levels of energy and distance?
So the correct answer, of course, is pulse width, just so everybody understands. So there's multiple pulse width. And like I said, that is one of those things that a lot of people were never explained that that's what it's doing. But the very first thing that I want you to do, if you did not know that when you go back to your TDRs, investigate, okay, so how does this actually work? How do my pulse widths work? How am I able to change that? Typically, you'll have a pulse width button, but also what you will probably have, depending on which TDR you're using, there's also going to be some sort of automatic range feature. So sometimes if you have, like let's say you start off in 50 feet, most TDRs will automatically start off in the smallest pulse width available. But then as you bring on more cable, let's say you get to 100 feet and then you get to 200 feet, it may change it from possibly a 1 nanosecond pulse width to maybe a 25 nanosecond pulse width. So one of the reasons why people tend to miss problems is because the TDR, as you automatically add more cable, it's also automatically giving you more signal whether you want it or not. So sometimes you can get to a cable that's 1,500 feet or 2,000 feet long. It's giving you a pulse width that'll get you 2,000 feet long, but accidentally overshooting everything in the very beginning. I should go into that a little bit more, but for right now, that's all I have time to do. So let's talk about another example that happens to a lot of people by telling you a story. I was deep in the heart of Texas a couple of summers ago, and I'd done a couple training sessions for a bunch of guys, and we had about 20 or 25 people in this class. They bought a bunch of my TDRs. We started off at 8 o'clock in the morning, kind of just like we did here. It's in the middle of the summer, somewhere near Fort Worth, and they said, hey, Chuck, what are you doing after this class? And I said, oh, that's sweet. My Texas boys want to take me out to lunch. No, they didn't want to take me out to lunch. What they wanted to do was get me out in the field and see if I could do what I said I was going to do. And I said, all right, bring it on. So they had this section of cable that had been bothering them for a long time, and they asked me to take a look at it. Oh boy, how beautiful is that? So they took me to this MDU. Now, first of all, full disclosure, we were not shooting inside this rat's nest. We were actually shooting out across the yard of where this apartment complex was. So we disconnected right here, and we're shooting out across the yard. Now let me paint the picture for you. While we're connected at this apartment complex, straight across the yard that way, we go straight down about 3 or 4 feet in front of, about 5 or 6 feet in front of us it's going under a sprinkler system. And then it's going across this yard. 300 feet that way is the pedestal. But before we get to the end of the pedestal, there's a driveway that goes underneath the concrete. So that's what's giving you, that gives you the view of what we're dealing with here. And this is what the waveform looks like. So if you've ever used a Springbok TDR, this is what our software looks like. And again, I want to point out that if there's any waveforms that you want to send me and ask for my help on, I don't care which brand of TDR you're using. I'm here to help. If you're not using a Springbok TDR, we'll worry about that later. So this is what I want to show you what we're looking at first of all. This is my output pulse. This is the end of my cable at 331 feet. I only have 80 feet displayed right now, so the first thing that I'm going to do is go to my range feature. Remember, that's my more cable, less cable key. And I want to bring that end of the cable on the screen. Yes, I saw that too. So this is the end of my cable where it's attached at the pedestal at 331 feet. This is just a zoomed in version of this. One of the things I should have pointed out earlier, hopefully most people realize this, this is my output pulse, or where the signal starts. That's the BNC on the front panel of my TDR right here. The reason my first cursor is right here is because that's where my jumper is. So if I'm using an 8 or a 10-foot jumper, instead of measuring from right here, my now 0 point is right here. That's called zeroing out your jumper. So as I get connected, and this is what I'm seeing live, of course I uploaded this to my device, as I see, the first thing that I see are these two obvious humps over here at about 184 feet. So I asked them about that, and they said, yeah, that's a block splice. So we know about that, and we know that that's not what's causing our problem. I said, okay, we're good. Now, when I get closer to the front over here, the next thing I notice is two events right here. I'm going to call rather obvious. So if I take my second cursor over here and I measure to that, see where my green window is right there? I see something at 4 feet, and I see something at about 8 feet. So I asked them, is there supposed to be something at 4 feet and 8 feet? Did you guys see that before? And they asked me, do you see something at 4 or 8 feet? And I'm like, hey, who's asking the questions here? Sorry, I don't mean to panic, but the reason I'm panicking is because we're out there in 110 degrees, not exaggerating. I swear to God, I didn't think it was going to be this easy. So I said, yeah, I actually do see something at that distance. And they said, okay, then let's get out the shovel and dig it up. And I'm like, yeah, why not? It's 110 degrees. What do I care? So before we get there, because now I didn't think we were going to do this today. Don't get me wrong, I know what I'm doing, but I'm panicking a little bit. Okay, because I really want this to be right. So the very first thing that I'm going to do is make sure that my cursor is exactly on the front leading edge. If I'm the one digging the hole, these are the things you need to keep in mind. Make sure my cursor placement is exact. Make sure you know how the temperature can affect VOP. It's 110 degrees in Texas, for crying out loud. That's going to be a big difference, right? Also, I look at my VOP, whoops, This is not a VOP of 80 cable. This should be VOP of 88. That's going to put my distance off a little bit. Now, in this short distance, not that big a deal. But understand, if I were off 8 VOP points at 2,000 feet, that's going to mess with my digging, right? But nonetheless, if it's worth doing, it's worth doing right. So I see at 4 feet, there's an issue. Now, the funny part about this is that these guys know their stuff. They're just as good at cable technicians as we have anywhere. We go ahead and take our shovel and start digging. And by the way, 4 feet is going to be right there, basically where I'm standing. We're just on the side of an apartment building, right? So I'm sitting here thinking, who was doing the testing here, right? So we start digging, and we're following the curve of the cable very gently right here. We're only maybe a foot into the ground at this point. And sure enough, just like I said earlier, right where that starts to curve right here, we shake off the dirt, we look at it, wipe off the cable. Sure enough, we find a hairline crack right there. And it was easy to find. Check this out, though. What pulse width did I shoot that in? A 2 nanosecond pulse width. I promise you, a 25 or better would not have found it. Anything higher than a 25 would have also shot right over it. So I know how they missed it, right? But nonetheless, we find that and we fix it. And then they say, didn't you say you found another problem just a little further in? I said, I did. Now I'm feeling confident. And I'm saying, yes, I did. It is at 9.74 feet. So if you're keeping track at home, we had just about 3 or 5 feet out of water, a sprinkling system, right? So we go in just a little bit further. We dig the hole. Full disclosure, we saw nothing right there. So we got to make a choice. We're going to dig a little further this way, dig a little further this way. We went just a little bit further that way, and sure enough, we found the splice. That was undocumented. I bet that never happens, right? And we go a little bit further, and we see this splice. Honestly, from here, it looks pretty good until we cut it open, and it's all nice and white and powdery on the inside. That is what this second one was here. Easy enough to find if you know what you're doing, okay? So a couple things I want to point out. If you are using the Springbok TDR, and I got to get a little bit industry specific here, whenever you get the opportunity, whatever TDR you're using, store it. Store it so you can justify it later. Of course, you're going to have to do that if you need to prove it. But if you want to get somebody else's help or send something to me to see if I can take a look at it, sometimes I can help you find the problem. And even if I can't help you find the problem, I can also help you improve your system. I can look at it right away and say, dude, you shot this in 100 nanosecond pulse width. All I can see is the end of the cable. But store it and then take a look at it later. And if they have a way of, if you have a software version with it, use your software, because there's reasons why that can help you as well. So check this out. So we found that this was the problem. Everything was cool. We fixed that as well. If you're using my software on the computer versus the app, this is another one of the things that we give you the option to do. Give me just a second here. This wasn't set up like I needed it to. My manager that I was dealing with at the time, he said, this is great. He says, you stored all this, right? Can you send this to me later on when you get to where you're going? And I said, oh, yeah, absolutely. So on the computer, I'm able to overlay multiple waveforms at one time. So I was able to just write him a quick report and let him know on the first line, this is what it looked like before. We repaired it, and this is what it looks like now. You have that option, right? Now, I also want to show you, back to my vertical gain question again. Check this out. This was even with my vertical gain all the way down. If I start to gradually increase my vertical gain, you see what I mean, how it can start to make my line look uglier and uglier? Again, this is where it's maybe just right. This is where it's obviously too much. A couple things I need you to understand about this as well. See how this line really starts to get ugly? And you see how there's all of this other residual stuff? I have to tell you, and many TDRs do this, the old tempos do this a lot. Sometimes as you increase the vertical gain, the line skews one way or the other. I need you to understand that doesn't mean anything. The fact that this line tilts on the second half of the cable, there's nothing I can gain from that. even all of these little spikes right here, does that mean anything? Well, my question is, isn't it obvious that this stands out first the most? Actually, this did, but they told me this wasn't a problem. And then this stands out the most. Worry about that first. Honestly, these are probably nothing. What are they? I don't know. I don't really care. Now, this is what I would have liked to have done. They told me there's nothing wrong with these block splices right here. But my spidey senses tell me that this could possibly be your next problem happening. I would have loved to have seen what this looked like from the other side from here. And if we could have got to this, I would have loved to see what this looked like from this side. Does that make sense? Okay. Now, all right. I'm doing well. Woody, I think we're ready for our last question.
Yeah, and I thought I had a question here from the audience, but for some reason it's not showing up. So I apologize if you submitted a question. I'm not seeing it. When I clicked on it, it went away. So let's get back to the poll.
Maybe we answered it.
Yeah, maybe we answered it. I'm going to try one more thing here. Nope.
Go ahead.
Okay, so when you enter the correct VOP, please select one of the below possible answers. The pulse width is automatically entered. The blind spot is eliminated. Attenuation is lessened. The instrument is calibrated to the cable under test. So we are collecting responses. I hope. I don't see any. Oh, there we go. Now I'm starting to see them come in. So apparently there's a little bit of delay. I'm going to go on mute and just hang out a second.
All right.
Okay, we got about 45% voted. We'll wait a little bit, so hopefully we can get over 50% here, or we stop the poll.
While we're doing that, so I mentioned earlier to everyone that I am in Lincoln, Nebraska right now, where it is 18 degrees. I'm hoping you're someplace warmer. Yesterday it was 15 degrees, so we're trending upward, but I'm not buying it. I'd rather be someplace warmer, and I'm going to Toronto tomorrow. I'm not that bright. Woody, what's going to be your high today where you're at?
Oh, probably 65.
Okay. Is it a nice 65 or a cool 65?
Well, the wind's blowing, I don't know, 50, 60 miles an hour, so depends. If you're in the wind, you're probably feeling pretty cool. So here's how the audience answered. When you enter the correct VOP, the pulse width is automatically entered. 6% chose that answer. The blind spot is eliminated. 6% chose that answer. Attenuation is lessened. 6%. So we had an even split between those. But lastly, the instrument is calibrated to the cable under test. 83%. So quite a few folks know what they're talking about.
So that obviously is the correct answer. That is why VOP is important. One of the things I also want to point out about VOP, even though I mention it early and often, truthfully, it's the last thing that I worry about, just like I showed you on that cable, because if I can't find it on the screen, nothing else matters anyway. So VOP is very important. It is the most important thing. It's something that not only that I typically worry about last, not first, but also VOP is something that you can change after you store the waveform. So when you go to recall it on your TDR, you can change the VOP then. When you upload it to your phone or when you upload it to your computer, you can change the VOP then. Similarly, if it's like, now wait a minute, he shot this when? Oh, it was 115 degrees that day. Let's see if we can adjust for what the temperature ought to be that way. Okay, you understand? So VOP is very important, of course, but keep it in perspective. So another one of the things I want to point out with a TDR, so we have a basic understanding of pulse widths. I do want to point out for those of you that are using the Springboks and why this is a definite advantage, a couple things I want you to understand. I want you to use 1,000 feet as your guideline for what I call long cables or short cables. Anything under 1,000 feet is what I call short distance testing. Anything over 1,000 feet I'm calling longer. In cable TV, we rarely go above 3,000 feet because of the amplifier spacing. But some of our TDRs, by ours I mean all of us in the TDR industry, some of our TDRs are made for the most extreme cases, like Australian Telecom. We have TDRs that quite literally can see out 4 or 5 miles. So when you see some of these TDRs that have distance ranges of 15, 20,000 feet, that's not a myth. They really can go out that far. But when I say using the 1,000 feet as a cutoff for your short or your long, if you are trying to save yourself time and this is something you need to turn into your supervisor for approval, I'm going to ask you to take at least 2 shots, right? One from point A to point B, and then also one from point B back to point A. But if it's a longer distance cable, I'm going to want you to shoot it in 2 pulse widths from each side, okay, and store it. Use one of your smaller pulse widths, 1, 2, or 5, and then shoot it again in one of your longer pulse widths, 5, 20, or 50, or 100, or something like that, so you can get everything close and then everything far. The reason why I bring up the Springbok at this point is because it's a time saver in that whatever all pulse widths that TDR has, it stores them all at once. So if you send me a waveform that you shot in 100 nanosecond pulse width, I'm going to ask you, I need you to go back and shoot it in a 1 or a 5 because I'm not going to be able to see anything from here. That costs you more time. That costs the company another truck roll. So make sure you always know what your pulse width is. Start out small. The cool thing about the Springboks is that it shoots it all in one shot, and I will show you why that's an advantage here coming up. This is just a really basic shot where I was dealing with one of my buddies in Salt Lake City, obviously a Comcast system, and he didn't know exactly what he was looking for, and I can't remember the details of what the system was doing, but for all intents and purposes, this is all he could find on this cable. If you recognize this signature at the end, that is an active, okay? Probably an LE. This was shot in a 2 nanosecond pulse width, shot in a 2 nanosecond pulse width, at least that's what's displayed, right? So as I start to increase my vertical gain, you can clearly see that the whole line gets ugly, but even when I start to get about here, does anybody notice that this is starting to stand out just a little bit and this is also starting to stand out just a little bit? So check this out. By using your zoom windows right here, the question becomes, does this stand out from the rest of the cable? That is very minute and very minor. It is hard for me to tell from this vantage point. And then when I get over to this first one, same thing. Does this stand out a little bit or not? Well, there's different ways to get that to stand out, but understand, this is where it starts to get a little bit hairy. But check this out, and I reminded him of this later on. This is shot in a 2 nanosecond pulse width, right? But also, all the pulse widths are automatically stored. I always want you to start off small and work your way up, but look what happens when I change this from a 2 to a 5. Because it's more energy, look what it does to the entire line. This all of a sudden makes this stand out a little bit more. So again, the question that I'm going to ask you is, does this stand out from the rest of the cable, yes or no? As it turns out, both of these happen to be wet splices, corroded splices, and that was the problem. All he had to do was just hit store, send it to me, and we were able to determine that as if I were connected live. Totally kick-ass, you feel me? I'm sorry, I said ass. Oh, right there, I said it again. Okay. Now, I'm going to show you another example, and then we're going to call it a day. Oh, this is awesome. This is one of my favorite ones. 2 years ago, I'm at a trade show in Indianapolis. Who cares why? Doesn't matter. That's just where I was. And I got this guy that calls me up. He's using one of my TDR Tracker Pros. And he says, Chuck, you got time to help me with this question? I'm like, absolutely. Talk to me. He says, well, give me a second. And this is what he did. He stored this on his TDR. We have an app that you can use on your phone. We also have the software you can use on your computer. He was at his wit's end trying to find this problem, but it seemed like there was obviously something there. I told him, call me if you need anything. He did. So our units are Bluetooth, which means you can Bluetooth it from the TDR to your phone. He sent it to me while we're talking on the phone. I wait for this to get to me. I've got Tracker View on my app so I can analyze it on his phone while he's got everything reconnected. I said, first things first, what problem do you think you're having? He says, well, before we go there, I got to tell you, the issue that I have is that my line is really noisy as heck. Now, understand, he had no AC and he had no RF on the line. And I get that I have my vertical gain turned up all the way here, mostly all the way, right? But you're seeing this ugly line all the way through, which looks like there's some sort of interference, but there's not. And I says, do you know what type of problem you're looking for? Do you know what you think it is? He says, I think I got water in the cable somewhere, but nothing is getting to stand out to me. And I think I have squirrel chews. A lot of squirrels in this area. I'm like, okay. First of all, I'm assuming this is aerial cable. And he says, it is. Okay, well, first things first, if you suspect that you have squirrel chews or cracks in your cable, the reason why it's so noisy is because the mere fact that you have an aerial cable, it's an antenna. If it's got cracks in the cable, it's just letting interference in. If you're near a city center, it's going to be ugly. If you're near an airport, if you're near cell towers, if you're near a railroad, there's so many things, an interstate, there's so many things that can make it pop out like that. But give me just a second while I analyze this, and this is the way I also want you to think of analyzing your waveforms. This appears to be the end of the cable at 1,500 feet, but as you see, I got 90 feet of cable on the screen, so I'm going to go over to my range, which is my more cable, and let me put the end of my cable on the screen. And by the way, if you are using the Springbok TDRs and you have not downloaded the app yet, shame on you. Do that starting today because it's going to be a life changer. So again, we see this, we recognize this earlier. This isn't active, okay? Can a TDR see through actives? No, it cannot. So we know that's the end of the cable. So I tell him, I see your LE over there at 1,500 feet, right? He said, yeah. I said, okay, give me a second. Keep in mind I'm doing this on my phone. So as I slowly start to increase my vertical gain, I'm going to stop right here. Actually, I'm going to stop right here. No, I lied. I'm going to stop right here. Does anybody see what it is I see? Right about right here. I see this, maybe this. I see this, and I see this, standing out slightly, okay? This is the harder stuff that I'm talking about. This is not the easy stuff to find. Couple things. In a 2 nanosecond pulse width, if these are small problems we're looking for, that's my best shot at finding these, right? So the thing that I like the most about my software versus my computer is something that I call my continuous range. Because I have my slider key for my range here versus set notches, it allows me to zoom in and zoom out at a free range, if you will. It gives me this flexibility where I can find that sweet spot. Because check this out. If I go just a little bit too far, I kind of lose it, right? But I can get into just a certain sweet spot here where I can see a pattern. So the first thing is I go to him and I say, what about that event at 443 feet? Now, between me and everybody else that's on the line right now, especially if you use your zoom window here, does this stand out from the rest of the cable? See, I believe it does, especially since he's already taken a look at this and couldn't find anything. So I hear him kind of swear underneath his breath, and I'm like, what's going on? He says, I've been out here looking at this for like 10, 15 minutes, and you find this right away? I'm like, well, first of all, I don't know that this is anything yet, but the truth is, you guys, second set of eyes, okay? He is out there working in the hot sun. Admittedly, on this day, I am not in the Texas sun. I'm inside a convention center waiting for a show to start. Fresh set of eyes. This is why you guys need to use the software as much as you possibly can, because even if you can't find something, you're outside and your fingers are freezing, send this to somebody else and see if they can find it where you can't. Second set of eyes. So he says, yeah, I see that now. And he says, and now I see, I said, I know, right? I see this event over here at about 389. I see another one at 338, and I see another one over here, possibly. I said, okay, so tell me this. What's your next move? He said, well, now that I see that, I want to get out there in my bucket truck, start to feel around, see if I can find something out. I said, bet. Call me as soon as you find out, which he did not, but that's neither here nor there. So as I'm looking at this a little bit further, this is the first thing that I was wondering. This is goofy to me. Look at the pattern. I'm wondering, is it possible that these are ghost reflections? And by the way, I don't think they're ghost reflections, but let me tell you why. Ghost reflections tend to happen the most at greater distances, but these look like they're so close to exactly the same distance apart. And by the way, this is when it becomes key. Look at my zoom window right here. This spot right here is perfect cursor placement. You understand? I measured each one of those perfectly at the very beginning of where that shape starts. And this is the funny part for me. They were not exactly the same distance apart. They were close to the same distance apart, but not exactly. Ghost reflections have no choice but to be exactly the distance apart. There's no fudging on that. That's basic math. So I send this to another buddy of mine in another state, and I say, what do you make about this? And that's the part that I bring up to him. They're not exactly the same, but they're close. He says, what's their pole spacing down there? I says, I have no clue. Why do you ask? And he says, well, because if these are squirrel chews, squirrels tend to chew right around the pole, maybe a little bit this way, a little bit further that way. That could explain why they're close, but not exactly the same. I'm like, oh, did not know that. This is why I love cable guys, right? So I'm waiting for him to call me back. The very following week, I'm in another city. I pull this out, and I'm thinking, he never called me back. But let me take a closer look at this again, because maybe I can use this in my next class, right? Check this out. I noticed that I could see everything that I needed to see in a 2 nanosecond pulse width. And again, going back to my vertical gain, it's a little bit too noisy. This is where it seems to make about the most sense. It never occurred to me, look what happens when I change this from a 2 to a 5 nanosecond pulse width. Because on the Springbok, I can. I don't got to be out there live. Because of the frequencies, this stands out cleaner with a 5 than a 2. Did you see that? Let me do it again. That's a 2. That's a 5. A little bit cleaner, right? But then, just for kicks, I decided, let me see what this looks like in a 20 nanosecond pulse width. Oh my God. I should have started here. This is the most obvious problem. Even I got stuck in thinking that you start with a 2, but the 2 is not necessarily the best. Because of the energy, it could be a 5, it could be a 20. But the whole point is with one of these TDRs, you only got to store it once, analyze it later. Add that to being able to send it to someone else with a second set of eyes. That is how we all get better quicker together. Also, check this out. When I did go from a 5 to a 20, did anybody notice that this also kind of popped up a little bit? That could be my next problem, but let's start out with the most obvious here. Okay? So, pretty cool how using all of those together works. So, one more thing I'm going to finish with my TDR top 10 and then see if we have any questions. A lot of slides. Okay. Work. Chuck's TDR top 10 rules. 1, read the operator's manual. If it comes with one, read your operator's manual. If you don't have one, call me. I can probably find one. 2, know your TDR. Probably stands to reason. Anything that you use, and this applies to all your test equipment, the more you know it, the better you're going to do. And one of the things I like the most about my particular TDR is that, at the very least, if you know nothing, learn to store a waveform, because analyzing stored waveforms later on, it can get you up to speed so quickly. Get as close to the fault as possible. Of course, I'm always going to tell you to shoot from both sides, but I'm also going to trust my distance the most from the side that I can get closest to my event. Make sure you make a good quality connection. I didn't spend too much time on that, but usually when I do TDR sessions in person, we can go into this more. But this is kind of meant to be more of an overview. Velocity of propagation, I think we beat that horse to death on why VOP is so very important. Make sure you begin in the shortest pulse width possible and then work your way up. Again, test the cable from both ends. Make sure you determine your cable path and depth. I can tell you with reasonable certainty that you have an event at 242 feet, but you still have to find where 242 feet is. Retest after repair. And not only should you retest after repair, but if you do dig into the cable and fix something, while you're there, connect, shoot this way. While you're there, connect, shoot that way. And then, of course, use common sense. But as my mother used to always say, sense was never that common. Okay, we have reached the end. Do we have any
I'd have to agree with you there. For me, sense isn't that common. So outstanding job. I don't see any questions, but outstanding presentation. If you didn't know a lot about TDRs already, you probably know a lot about metallic TDR. And if you were already expert, you probably found some things that you didn't know too. So thank you so much, Chuck. I'm going to do something I don't usually do. Let me because this presentation will be archived. And what I didn't realize is SCTE changed the way they archived events. So I don't know what screen you're going to see when I pull this up, but I'm going to show you if I can. And I just lost it. Here we go. Let me see if I can present this and show you where to find it. Show my screen. So which screen are we going to see here?
Do I need to stop sharing? No.
I don't know what you're seeing, so let me see if I can move. Do you see events calendar here?
I do. I can see what you're doing.
So if you go to, let's say, for example, we had a really good event in December. So if I go here to this CA Chapters Training and Summit, and I click on that and load it, you will see watch replay here, right? So you have to go back in time and you find the event you want to view, and you can watch the replay. Now there is a kind of a registration to simple registration to review or watch this recording. So if you have folks that have missed this and want to see this, give a little time. Chuck has already provided permission for us to re-air this. So give a couple weeks, and today's presentation will be available for those who would like to view it.
Woody?
And yes.
You have to be an SCTE member to view archive videos.
You absolutely have to be an SCTE member. So that is one of the benefits of SCTE members is that you can go back and you can review any of the webinars that where the presenter has provided permission to re-air it. So please, if you're not a member already, please think about joining. And for those that are part of the All Members Cable Labs groups, which most of our major MSOs are members, you can get in for absolutely free. And I think for everybody, it's automatic renewal. So you'll get renewed every year, and as long as you're employed with that company. I will also say I do see that Pete Zarelli is on. Pete Zarelli does an outstanding presentation on OTDR, and we're working with Pete right now to get Pete on again to do a presentation again coming up soon. I think it's in March. So we'll get that going. For now, I just want to say thank you again to Chuck, and thank all the audience for joining, and we'll see you again soon. Thank you,
Thank you all.
everybody.
Bye.